everyone, welcome to the mind map series. And in this particular mind map, what we are going to discuss is this chapter, atoms and nuclei. So we'll start with the like a couple of centuries ago. I think it was proposed that atoms are the smallest functional and indivisible unit. After that, people started to give models of atom, like what is the structure of the atom. The first model was the J.J. Thomson's model. J.J. Thomson. He said that the whole atom is a positive charge, evenly distributed positive charge, and there are electrons embedded in it. Particular point charges, electrons embedded on it, such that it becomes effectively neutral, but it is like a common whole, a common charge, mass charge, and these are point charges, electrons, and they combine to make an atom, electrons and protons. So this was called plum pudding model. And then came the famous Rutherford's experiment. So what Rutherford, actually a student of J.J. Thomson, did was, at the time alpha particles were already discovered. Alpha particles. What are alpha particles? These are basically helium nuclei, He 2 plus. Basically all the electrons of the helium stripped away, and only the nucleus of the helium is there. Now what he did was, he prepared a very thin layer of gold sheet, a very thin layer, right? Such that the if you look at it from cross section wise, you might have very few amount of atoms in the width. So that, yeah, this could be one representation of the uh, Rutherford's experiment. Now what he did was, he fired alpha particles into the gold foil, very thin foil, such that the thickness has only a few atoms. Now what he observed was, most of the alpha particles pass through it very easily, almost 99%. But some of the alpha particles get deviated. Some particles get deviated, and some particles deviate even more, and some particles deviate so much that they almost come back, and some particles, very few, they come exactly back, go straight and then come straight back. So this was the basic this observation of Rutherford. He found that most, like more than 99%, passed straight. What he concluded from there is, if the atoms had no deflection, or the, see, what is this alpha particle? It is basically 2 positive charge and 4 mass, right? Nothing else. 4 unit atomic mass and 2 positive charges, because there is no electron in it. And if it is getting passed from certain portion of the area of the atom, then it is quite clear, right? If it is not deviating, even if it was an electron or proton, it would have interacted with it because of Coulomb's law, Coulomb's interaction between the forces, or between the charges, k q1 and q2 upon r square. But most of it didn't happen. So what he said was, probably most of the space inside the atom is empty, and the positive charge is concentrated over a very small volume of the atom. So the first observation was, most of the atoms are empty. It's like a giant sphere At the very center, there is a small dot of mass, and the whole sphere is hollow, empty. So, what he gave from there was Rutherford's model, and he said that protons are concentrated at the center while electrons rotate around the around the n- proton. Sorry, nucleus. There is a nucleus, and electrons rotate in fixed orbit around the proton. Sorry, nucleus. So this was Rutherford's model, but it also had some uh, imperfections. See, this was Rutherford's alpha particle scattering experiment. Alpha particle bombarded on the gold file. Most of the alpha particles pass undeviated. Yes, one out of deflected by scattering means 1 out of 8,000 alpha particles get deflected slightly. It means like 799 alpha particles pass straight away. We also discussed about Thomson's model. Uh, what he also gave was a formula which is not difficult to remember. I think it has been used a few times. That what is the closest approach, closest distance of approach. Let's say this is an atom and this is a nucleus, and you fire alpha particle from here, and in such a manner that it approaches straight to the nucleus. But that would not happen, right? Because alpha particle is a positive charge, nucleus is a positive charge. As the two come together, the force of repulsion between them will grow even stronger. That is why the alpha particle after certain point will get repelled. So the closest amount of distance from the nucleus r that can be achieved by the alpha particle can be given by this formula, this particular formula. B, impact parameter, or closest distance of impact, where z is the number, atomic number, and cot 5 by 2, it means what is the angle of interaction. Let's say this is the nucleus, and let's say you are coming from here, then the angle, right, theta, from here you will get deviated. So what is the angle at which they are there, theta. So you'll have to place that here, and 4 pi epsilon naught is a constant, and half mv square is basically kinetic energy of the alpha particle, of alpha particle. All right, so this is the formula that you might keep in mind. So now Rutherford's model, atoms have a central massive positively charged, that's what I said, around which electrons revolve. Size of the nucleus he gave around 10 to the power minus 15 meter. Based on the very less interaction of the alpha particles, he probably came to know that since most of the atom is empty, what should be the amount of area around which uh, scattering is happening. So based on that, he gave the size of the nucleus in the range of 1 Fermi meter. Now, drawbacks doesn't explain the stability because, see, um, you might know that when charges revolve, they emit electromagnetic radiation. When the charges accelerate, basically, uh, see, the charges are revolving inside a circle, and when inside a circle, the centripetal acceleration is always acting on the electron, and that is why, as per Maxwell's criticism on this theory, मैक्सवेल ने क्रिटिसाइज किया कि अगर बेसिकली इट इज़ अ बेसिक रूल दैट अगर कोई भी इलेक्ट्रॉन या फिर कोई भी चार्ज एक्चुअली एक्सलरेट करेगा तो उससे इलेक्ट्रोमैग्नेटिक रेडिएशन निकलेगा निकलेगा. So if electromagnetic radiation is coming outside of the or getting emitted from the electron, then the electron is losing energy basically. Then it should continue, if it continues to revolve, it should eventually collide into the nucleus, right? This was the criticism of Maxwell, which is why we have another model doesn't explain the atomic spectra. This we will talk about in the slightly later part of the mind map, atomic spectra. Now I think this is also clear. Now comes the main model, which is Bohr's model. In the I think year 1932, Niels Bohr gave his model of atomic structure, in which he defined that let's say this is a nucleus, and around which you have different energy levels. What he defined was you have different energy levels, and the energy on these levels are defined. And whenever you absorb energy, or the electron absorbs energy, it will jump into the orbit next to it, or some other orbit which is on the upper side. And he also gave particular velocity as per the number of atomic number in the nucleus of the nucleus, and the number of shell as well. So he gave velocity, he gave energy level, and he gave a few parameters as well. So one of the basic parameter, or the basics of Bohr's model, is the quantization of uh, angular momentum. Angular momentum is always quantized. What is the meaning of quantization? Is basically that whatever angular momentum of an electron can exist, it should always be in a multiple of a certain constant. Let's say there is this constant 1, then every number has to be in a multiple of 1. I'm just taking an example that the very smallest angular momentum possible is 1. Then all the angular momentums of all the electrons will be in the integer of 1, 2, 3, 4, not like 2.5. Okay, so this is basic meaning of quantization. I just took an example, it is not exactly this one. तो क्वांटाइजेशन ये हो गया. अभी बोस मॉडल में भी इसने सेम कहा था कि इलेक्ट्रॉन रिवॉल्व करता है इन स्टेशनरी ऑर्बिट. आई डिड टेल यू राइट, स्टेशनरी ऑर्बिट्स, दीज आर कॉल्ड energy levels. And as per the angular momentum, what is the angular momentum? mvr is equal to L is equal to n into this constant h by 2 pi. So h by 2 pi is the basic smallest angular momentum that can exist, and n is the number of principal quantum number. Yes, principal quantum number. All right. Now, so this is the quantization of angular momentum. Now, it also explains the, yes, hydrogen. And so basically for Bohr, we'll talk about in the limitations that Bohr always talks about that whatever may be the atomic number, whatever may be the number of protons and neutrons inside the atom. But as per Bohr's model, it explains the situation only for when only one electron is there inside the system of the atom. It means if you have a carbon atom, of 6 protons and 6 neutrons, then you will have to get rid of the 5 electrons, and only one electron should be there. Only one electron should be there. Only then this Bohr's model can be applied to the system. Otherwise, it gets too complicated, and the Bohr's model cannot be applied on the system. But even in the case of one electron, it is still very uh, it was very revolutionary, this model, because it could perfectly explain at least one electron, what happens to the one electron. So Yeah, limitations, fail to explain the spectrum. We'll talk about the spectrum. Complex, see, complex atom. It fails to talk about the complex atoms. Complex atoms means having more than one electron. Z-man star effect, we do not need to worry about that, no. Now, he gives certain very good equations, and you have to remember them. Not in this form, but on the lower form. So, he gave, basically, just a second. Yeah. So, what he gave was particular very distinct formula, so that you always get to know that, let's say this is a carbon atom having six protons and six neutrons, basically say six atomic number. Then what should be the behavior of the electron around it, a single electron? For any number of number of protons or atomic number, he gave this particular formula. These and these are very important. The radius of the this thing, radius of the, let's say this is the nucleus and this is the radius of the energy level or the orbit, then it is equal to 0.53 into n square by z angstrom, where n is the uh, nth shell nth shell and z is the atomic number. Nth shell means whether it is in the, I did tell you, right, that there are different energy levels inside there is a particular nucleus. Then there are different energy levels. This is the first energy level which is possible, this is the second energy level which is possible, this is the third energy level possible. Basically, as per Bohr's model, the electrons cannot exist in between them. It has to be there or there. It cannot exist in between specific energy levels. Let's say this is the first energy level, this is the second energy level, this is the third energy level. So basically, if you have nth number of energy level, or the I think I should rather call it the nth shell, then you just place n over here, and the number of protons inside the nucleus, you just place it over here in the form of z. Then you will have the formula, this one. This is very important, the radius of the shell as per Bohr's model. You just have to remember this one, not this one. No, not really important. Then the velocity of the electron inside the shell, with what velocity it should rotate, that is given by this formula, 2.2 into 10 to the power 6 meter per second into z by n. Again, z is the atomic number and n is the nth shell. You have to remember this one. Whatever I'm marking over here, you have to remember them very, very religiously, because questions are solved in just a second if you have them in mind. Now, coming to, let's talk about actually the total energy, or let's talk about the potential energy. Potential energy is given by this formula, where it is dependent on z square by n square. Potential energy, you can also remember these things. R is dependent on n square by z, V is dependent on z by n, and potential energy is dependent on z square by n square. Now you have the kinetic energy, which is exactly half but opposite sign. This I think you might have noticed in the chapter of first gravitation and then electrostatics, that potential energy turns out to be double the kinetic energy in opposite sign. So this is what you have to remember, total energy, that is equal to this much. Energy is equal to this much. This you have to remember. Minus 13.6 into z square by n square. Z is the number of atomic number, and n is the nth shell, on which shell is the electron lying. And based on the difference of this one, you can find out the rest of the things. These are just for explanations and not really needed to remember, or actually it is very easy to remember. It's just that the total energy is equal to minus ke is equal to twice sorry, half potential energy, simply. So these are the things that you have to remember in this Bohr's model. And yeah, energy level they have already talked about. Let's say this is the proton, oh sorry, this is the nucleus around which the atom is there, and I have made two shells for now. Let's say the electron is there. Due to some reasons, maybe photoelectric effect or something, whatever is happening, it jumps into the second shell. It gains some energy and jumps into the second shell. Now, due to the electronic this attraction due to the let's make it here rather. Yes, due to the attraction to the nucleus, it will come back to its original form. But while coming back, don't you think it is losing some energy? Why? Because the energy on this one is equal to, let's call it hydrogen atom. Then the first shell, the energy is equal to z square by n square, right? So minus 13.6 electron volt. This is the energy on the first shell, and the energy on the second shell is z square by n square, right? So z remains the same for sorry, hydrogen atom, and n square is simply 1 by 2 whole, so 1 by 4, right? So that becomes 3.4, I think. Yes, 3.4 electron volt minus. Now what is the difference between them? It is simply 10.2 electrons volt, right? The difference of energy. So while coming back, don't you think it is losing energy of this much amount, 10.2 electron volt? It is, right? So what I will do is, this is the potential, this is the energy, right? And you have to convert that into I think joules, or maybe you can leave it here. This is equal to the energy radiated, right, in the form of light. When you have to find that, you will have to basically do hc over lambda, isn't it? Hc over lambda, because this is the amount of energy inside a photon, and this is getting released while the electron is coming down from the second shell to the first shell. So this is the emission related to the fall of electron to the other shell. So this, I think, yes, electron jumps from higher energy level to lower energy level. It releases energy in the form of light, and this is the energy that is equal to. So basically you have to do this thing. If you are in the second shell and you jump into the third shell and coming back into the second shell, then you'll have to find the difference between them, right? And this can be found out easily from this one, from 1 by n to n1 square minus 1 by n final square, and this will be equal to hc over lambda. And here hence you can find lambda from this calculation, basically the wavelength of emission. And based on this, there is this hydrogen gas released in a sealed tube. So basically there is a hydrogen atom, and they are talking about basically, yeah, so hydrogen atom, it has several shells around it, energy shells, and hydrogen already has only one electron around it. So you can easily apply the uh, Bohr's model in rest of the atoms. Let's say lithium, you'll have to uh, get rid of the two electrons, right? There are three electrons inside it. You have to get rid of them. So basically ionize them. Li plus plus or 2 plus. Only this will exhibit the properties of Bohr's model. This will not, because it needs a one electron system. अब ये हो गया, तो ये वन शेल है, फर्स्ट शेल, ये सेकंड शेल, ये थर्ड शेल, ये फोर्थ शेल. Now let's talk about Lehman series. basically it talks about um, from n1 to n final, which can be ever higher. So let's say the electron is here, and due to some absorption of energy in any form, it jumps to the either the second one, third one, fourth one, fifth one, sixth one, etc. While coming back, they'll come back, right? They will fall back. They might fall back like this or directly. Both can happen. And this could happen in this manner or in this manner. And then, so basically, whatever the original shell was there, it will come back. Then, while coming in all these fashions, this will amount to, this will release certain amount of energy, this will release certain amount of energy, this will release a certain amount of energy, and if all of them are different, then they will constitute a particular spectrum of uh, radiations, right? It will not be exactly one wavelength, it will be several wavelengths, whichever is possible in the permutation and combination that is possible. So this is called Lehman series. When the electron jumps from the first shell to any other shell, and while coming back to the first shell directly or indirectly, directly means from the final shell to the first shell directly, and indirectly means jumping to some other shell and then coming back to the first shell. So this is called Lehman series. You only have to remember this one. For Lehman, from n is equal to 1 to n final, which is any number of shell, basically jumping from the first shell, that will give you at the end Lehman series. What about Balmer series? It is just the same thing, that electron is there initially and it is jumping to some shells, let's say this one as well, and while coming back to the second shell, whatever energy that is released in the form of electromagnetic radiation, or this one, yeah, so all of them will be calculated, whatever the difference you just apply the permutation combination, and for each of the difference in energy, you just equate it to hc by lambda, and you'll get the spectrum, whatever wavelengths this spectrum will release, and that is called Balmer series. Paschen series, from third shell, everything having the same. So if you're getting excited from the third shell, you'll get to the higher shell, right? You'll not get excited and go to the down lower shell. So Paschen series for initially electron as third, and bracket for initially electron as fourth, p fund at initially electron at 5. It will only go higher, and while coming back, it will release photon or electromagnetic radiation, which is equal to the having energy equal to the difference in the energy shell, energy level of the, sorry, difference in the energy level of consecutive shells. This is called so these are particular series. You only have to remember this one. For Lehman series, n is equal to 1, initially the electron is where. For Balmer series, initially electron is at 2, because you do not have to remember all these terms. No, not really important. No, even if you are asked, you will be given certain amount of data that from there you can deduce, but you have to remember this one, that for Lehman series, initially electron is at first shell. For Balmer series, initially electron is at 2 second shell. This thing in the, for each of the series or the spectrum, that you have to remember. I think this part of the mind map is okay. Now coming to radioactivity, or actually nucleus, more of the nucleus, because this radioactivity has been removed from the syllabus, so we will not be talking about this one. Okay, actually, where is alpha, beta, gamma? It is also not important, but for general information, I'll just talk about it a little bit. But it is also has been removed from the syllabus. Radioactivity is a major portion which has been removed, so you do not have to worry about this at all. Now, some basics of uh, atoms that you might have, I think that was in ninth class as far as I can remember, isotopes, isobar and all. So isotopes is basically having the same number of protons but different time of neutrons. So C6 but having a different mass. If it has a different mass, basically the number of protons is the same, only the number of neutrons can vary. So neutron variable. What about the isobars? Isobars basically have the same mass but they have different atomic number, right? Let's say you have 6 proton and 8 neutron and 7 proton 7 neutron. They both combine to the same mass but they are different atoms. This is carbon, this is another one, nitrogen. These are called isobars. What about isotones having the same number of neutrons? You just have to have the same number of neutrons. You could have different number of protons. So basically isotones will never have uh, same same Z. No. For these, this one Z is same. For this one, number of proton is same. Sorry, the mass is same. Number of proton is same, mass is same, and this one neutron is same. This you can remember. Now, this is pretty basic composition, number of mass number and all. Not really important for us to discuss. Coming to this one, nuclear radius. Basically, what it says is, let's say you have a drop of water, and then you combined 1,000 number of drop of waters, then you'll get a bigger drop. What should the radius of bigger drop? If it has a radius of r, how can you calculate? You'll basically uh, make the volume constant, right? Volume constant. So 1,000 multiplied by v1 is equal to v2. So 1,000 multiplied by 4 by 3 pi r cube is equal to 4 by 3 pi r capital R cube. From there you will get r is equal to r to the power 1 by 3. This is what you will get. Applying the similar concept over here, the nuclear volume, this is basically applying the same concept. You will get in the form of this one. R is equal to some constant multiplied by a to the power 1 by 3. Alright. Where a is a constant, sorry, r naught is a constant. And a is basically the atomic number. Sorry, mass number. Not the atomic number because it has neutrons as well. Mass number, total mass in atomic units. And yes, volume, basically volume is dependent on the atomic mass number, because more the number of protons and neutrons, the more will be the volume. And density that they have calculated, the mass and the volume of the nucleus. This is not important. No, this you should remember, and this you should remember, the one that are in the boxes. Simply, you might even remember this one, R naught value 1.2 Fermi meter, or 1.2 into 10 to the power minus 15 meter. Now this one has been removed, alpha beta particles. I'll just talk about it slightly. Alpha particle, basically helium 2 plus. This is not what you have to remember. Just doubly ionized helium ion. Alright. What about the beta particles? Electrons. They are basically electrons. They have some penetrating power, but they are basically electrons. Electronic beam. These are called beta particles. Gamma particles. Gamma rays are actually electromagnetic waves having very high frequency. A wave having very high frequency, having no mass. Of course, it is basically photon, right? Just having higher frequency does not bend the properties of light. It is photon having very high energy, so that whenever it strikes any other atom, it gives it so much amount of energy that, let's say, an atom is there having certain amount of electrons. Then if a gamma ray strikes this atom, it will most probably knock out many of the electrons and it will ionize them. If the electrons are knocked out, it will basically get ionized, right? The atom. That is why this type of ray is called ionizing radiation, ionizing power. All right. So this has been discussed. Now only to the I think Einstein's this very famous equation E is equal to mc square. So basically, I'll give you this one in the other form. E is equal to mc square. This is the basic result of Einstein's theory of relativity. This basically talks about that for any amount of mass, it is associated with energy. It means a mass can have, or you can even imagine in this format that a mass is made of energy itself. Energy is mass and mass is energy. They are not different. It is just that one can be converted to another form and the second could be converted in the first form. Energy can be converted to mass and mass can be converted to energy. This is what happens in nuclear reactions. For example, this is an atom having 235 amount of atomic sorry atomic mass. Then it splits into, let's say, two different atoms. Actually, this is uranium 235, and it splits into, I think it used to split into, yes, barium and krypton. Crypt, uh, yeah, Ba and Kr, barium, and I think this is related to a lanthanide series. Anyway, so the both of them combined mass are actually not 235. It is 230. Mm, yes, 234. Where is that one mass going up? And how is it happening? Let's say for starting this reaction, you have to have uh, a neutron which will destabilize the atom and make it fission. This the reaction is called nuclear fission, and the number of neutrons in both of them is one smaller than the number of neutrons in this one, and this neutron has already been released. So from here what you get is one extra neutron, right? One extra neutron which will go ahead and collide into another uranium 235 atom, and this will result into a chain reaction, right? So this will split again releasing neutron which will strike into another uranium atom, and this is a chain reaction which will lead to a nuclear explosion or a nuclear bomb. This is what happened in the uh, nuclear explosion of Hiroshima and Nagasaki, if you remember from your history classes maybe. It was not exactly 235, it was plutonium. It was plutonium that had detonated. Even plutonium can exhibit this property, nuclear fission. So this is nuclear fission, and the energy emitted, see the difference in the energy is what? Sorry, the difference in masses is one neutron. So what you'll do is basically whatever in the reaction, the difference in the mass, what you will plug here, the energy released from the nuclear reaction is equal to the difference in mass into c square. So basically the mass of one neutron, whatever that is, multiplied by c square, basically 3.8, sorry, 3 into 10 to the power 8 multiplied by the same thing squared, and this is the mass of one proton. Although this is small, this is a very large number, right? And this is for only one atom. Any amount of a small amount of this matter, uranium or any other fissile material, will have a huge amount of atoms, right? And that is why the energy released is very high, and that is enough to flatten a city, I guess. So this is uh, nuclear fission, and I have discussed, right, from this equation. It is basically the difference in energy, difference in mass of reaction, whatever chemical reaction that has taken place. If it is leading to some loss of mass, then it will essentially be a nuclear reaction. This is the basically the summary of all these. You do not have to worry about them. You do not have to remember that uranium goes into barium and this kryptonium, or I don't exactly remember the this lantern series, but still it is not relevant. No, for exam, no. And this is also not. This is actually fusion. This is fusion. So basically, hydrogen and hydrogen fusing to give you a deuterium while releasing some energy, because it leads to, see, what is this? One proton and one proton, right? What is this giving up? Hydrogen of having one proton and one neutron, but it has only one electron, right? Electron is lost in the process, and that will lead to the energy released, that is equal to this much, 0.42 mega electron volt. The energy released in this is much higher, but it is actually lighter. Hydrogen is lighter and this is heavier, so it ends up to be more. It tends to release more energy per fuel, per kg of fuel. And this is what we have already discussed. You do not have to worry about what is this, all that. I just told you that the difference in the mass multiplied by c square, that will give you the energy released. Theory of relativity, I think this is one fact. It is not relevant from the JEE perspective. Henry Becquerel discovered radioactivity. Radioactivity is basically the let's say there is one nucleus. It gets disintegrated. Let's say it has a certain mass, 235. Then maybe it gets into 233 while releasing, or maybe 231 while releasing an alpha particle in between. So this alpha particle getting emitted spontaneously without anything, it is called radioactivity, radiation emitting. So I think this is mostly from this chapter, and that's all.